I would like to thank the organizers of CECC 2020 for inviting me to the conference to give and talk about authenticated encryption. So the main goals of authenticated encryption are, on one hand, confidentiality, as typically provided by block cipher modes of operation, as well as authenticity and integrity of the data transmitted over an unsecured channel, which is typically provided, for instance, by message authentication codes. In general, the interface of authenticated encryption is rather simple. So you take the key and the message in the most basic setting, encrypt this, and the result is a ciphertext, which guarantees the confidentiality of the message, and some tag, which is then used to verify the authenticity of the message and to protect its integrity. And then for decryption and verification, one takes the pre-shared secret key K, the ciphertext and the tag, and if the tag is correct, the message is returned, and otherwise no information is returned if the tag was incorrect. However, in practice, one typically does not use this very simple interface, but additionally, one often has some associated data, which is data which needs to be authenticated, but where the confidentiality is not so important. Typically, this could be, for instance, some routing information of packages sent over the network, which can be read but cannot be modified by some attacker without the knowledge of the key. And decryption again works the same way. You take the key, the nonce, the associated data, the ciphertext, and the tag, and you only get the message if the tag was correct. So in general, there are many ways to build some authenticated encryption schemes. The most obvious approach is to combine an encryption scheme like a block cipher mode of operation with some MAC. This can be done, for instance, by doing encrypt and MAC in parallel. So you take the message, you encrypt it to get the ciphertext, and you compute a MAC to get the tag. Or another approach is encrypt and MAC. Basically, you take the message, which is encrypted with some block cipher mode of operations, and then you get the ciphertext, and then this ciphertext is used as input to the MAC to generate the tag. And last but not least, one can also do a MAC then encrypt. Basically, you MAC the message, you get the tag, and this tag together with the message is the input to the encryption scheme, which then gives you the ciphertext and the tag. And all these three versions of general compositions are also used in practice. For instance, encrypt and MAC is, for instance, used in SSH. And the security of this general composition, of course, depends on the details of the encryption scheme in the MAC. Another option is encrypt and MAC, as mentioned before. This is, for instance, used by IPsec, which is also standardized by ISO, which is shown to be proof secure. If a secure encryption scheme and MAC is used, of course. And last but not least, there is the option of MAC then encrypt, which is, for instance, used in SSL and TLS, where again, the security depends on the construction of this encryption scheme and MAC and how they are interact. While general composition is some rather simple and easy way to achieve authenticated encryption, of course, this has some limitations, like you need an encryption and a MAC scheme, so two different primitives with two different keys to achieve authenticated encryption. And this was quite fastly noticed by the cryptographic community and resulted in the design of dedicated authenticated encryption schemes, where you can do both encryption and authentication at once with only one primitive and in particular with only one key. So for instance, ISO standardizes 6 authenticated encryption modes for block ciphers. So first of all, generic composition, encrypt and MAC, and then the most well-known schemes are CCM and GCM, which are also standardized by NIST, for instance, and AIX, which is an extended versions basically of CCM and OCP, which is very efficient but unfortunately standardized, which basically results in the fact that it's not very often implemented in practice. And last but not least, there is SIV or key wrap, which is basically very similar to deterministic encryption. But the most popular schemes employed in practice are CCM and GCM, since it's also standardized by NIST and, for instance, implemented in TLS. So CCM is basically MAC and encrypt with counter mode and CBC MAC, where you first take some nonce, and then the ciphertext is produced by doing a counter mode of operation for the encryption, and in parallel you do then CBC MAC, where the last block produces the tag, which is then again encrypted with counter mode. This is, of course, proven secure, assuming an ideal cipher, which is typically implemented in practice by using AES. It has the advantage that you do not need to implement a decryption function of the block cipher, since you use counter mode and CBC MAC. However, the drawback is that you need two block cipher calls per block of messages is processed. It's not online, meaning that the length of the message needs to be known before you do the encryption. And of course, the MAC computation CBC MAC is not parallelizable, which may result in some performance penalties on high-end platforms. Another very popular scheme is GCM, Galois counter mode, which is again encrypted MAC with counter mode and counter magma MAC. Here you do again counter mode for encryption, but the first block you encrypt basically 0 to get the value H, and then you do the text computation by using a G hash, which uses a large multiplication in the final field. This is very nice because the encryption is parallelizable. Again, you don't need any decryption function implemented, and now you only need one block cipher call per data being encrypted, since you use a G hash for the MAC computation. The disadvantages are, of course, that this multiplication is harder to implement, sometimes particular in hardware, which may result in some larger area for constrained devices. And there is, due to this multiplication, there are some weak keys in GCM which are well known for quite some time. All these limitations of GCM and CCM in particular when implemented on constrained environments, where you need either two block cipher calls or this G hash or one block cipher call for doing the encryption, lead to several initiatives for finding new authenticated encryption schemes which are more secure and more efficient than CCM and GCM in the last few years. And these efforts are mainly driven by the CISA competition, which was done from 2014 to 2019, which had the goal to identify a portfolio of authenticated encryption schemes that can be used on all kinds of different applications, offering advantages over existing schemes, which was mainly driven by the scientific community and can be compared, for instance, to the eStream project or NESTI. On the other hand, shortly after CISA finished, this started to do an competition for lightweight authenticated encryption with the aim to identify lightweight authenticated encryption schemes, particularly tailored for lightweight applications, which they plan to standardize next to the existing solutions for those use cases. So CISA was held from 2014 to 2019 and was organized in 9 rounds. and basically was seeking for new solutions for authenticated encryption for free applications. So the first use case was lightweight applications like IoT, RFID, smart cards, and so on. The second use case was high performance applications like high-end servers which have a very high throughput or dedicated hardware implementations. And last but not least, defense in depth, which basically refers to schemes which have some higher robustness by design against implementation errors or wrong usage of the authenticated encryption scheme. In total, there were very a lot of submissions, 57 submissions in the first round, and then this number of candidates was reduced over 4 rounds to 6 candidates, which were then chosen for the final portfolio of Caesar. So in each category, there were basically 2 algorithms selected, primary and a secondary choice. For lightweight applications, the first choice was Ascan, and the second choice was Acorn. For the high performance applications, there were 2 choices for the first recommendation, namely AGIS and OCB, which I have mentioned before, which was proposed by Rogaway several years ago, which has very good performance and nice implementation characteristics. However, has the drawback that there are some patent issues, which led to the fact that people are hesitating to use this scheme. And for the last category defense and depth, there were again 2 schemes standardized, selected basically, namely Deoxys 2 and Calm. And followed by the NIST competition, in particular inspired by the use case for lightweight applications. NIST decided to run an own competition with the aim to standardize authenticated encryption schemes for lightweight authentication. This started very close to the end of the Caesar competition and is still ongoing. And very similar to Caesar, they received almost 60 submissions in the first round, which was then reduced to 32 submissions after 1 year, and will be further reduced this year, uh, most likely in September, to a smaller set of candidates so that the scientific community can focus on analyzing smaller sets of schemes in the following years to ensure that the algorithm or algorithms that will be selected for standardizations are well analyzed before they will be implemented in practice. So currently, as I said, there are 42 candidates in round 2. Here I list all of them. All of them are having some particular implementation characteristics and security proofs. Some of them are based on block cipher constructions. Some of them are based on sponge constructions. Some of them uses 4-bit S boxes or 5-bit S boxes. There are constructions based on modular addition, XOR, and rotations. And so on. And it's now the job of the scientific community to analyze all these schemes for the security or to implement the schemes on different platforms like microcontrollers or hardware to compare the performance, to help NIST selecting a good candidate or a small set of candidates for the next round, to focus the analysis and implementations of those schemes to find a good scheme which will be then standardized by NIST. However, in this talk, I will not talk about all these 32 candidates, but I will focus on 2 different designs. The first of all, I want to talk about Ascan, which was the first choice of Caesar for lightweight authenticated encryption. which is a dedicated authenticated encryption scheme based on the sponge construction. And then the second part of my talk, I want to focus on ISAP, which is a mode of operation, again, based on the sponge construction, which allows to achieve some robustness against implementation attacks already on an algorithmic level. ASCON was designed by Christoph, Maria, Martin, and myself. It was designed in 2014 as response to the CISA competition. It basically consists of two family members, ASCON 128, the first recommendation, and ASCON 128A, which is a faster variant of ASCON with a slightly lower security margin. And for the NIST standardization process for lightweight authenticated encryption, we added two new primitives, namely ASCON hash and ASCON XOF, and extendable output function, which basically allows lightweight hashing with a very low overhead compared to the authenticated encryption schemes. The main design goals of ASCON are, of course, security and efficiency on both very constrained devices like RFID tags or um, IoT devices, as well as high-end servers. It should be very simple to implement, following a very clear and easy description of the algorithm, and scalable for a wide range of platforms. Of course, it's single path and online, so that you don't need large buffers in lightweight applications. And one of the main design goals of ASCON is to provide sectional robustness with a very low overhead, allowing you to do secure implementations on IoT devices at a very low cost. ASCON is a non-space authenticated encryption scheme with associated data, as discussed before, and it follows the sponge construction proposed by Daman et al. In the design of SHA-3, and later on for authenticated encryption also in the CISA competition. ASCON provides a security of 128 bits and operates on a 320-bit state, and the capacity is either 256 bits for ASCON 128 or 192 bits for ASCON 128A, and the rate is equally 64 bits or 128 bits. The working principle of ASCON is very simple. Basically, the encryption process is split into four phases: an initialization phase, then the associated data, which needs to be authenticated but not encrypted, is processed, then the plain text is processed and encrypted, and then in the finalization, a tag of 128 bits is generated. In the initialization, the 328-bit state is initialized with IV, which is used for domain separation of the different primitives, a 128-bit key K, and the nonce. And then the ASCON permutation is applied in 12 rounds, and then after the initialization, the 128-bit key is again XORed to the capacity part. And this second XOR of the key sets the ASCON construction apart from the common sponge construction, where the initialization is only keyed once in the beginning, and this second XOR with the key is typically not done. Then in the second step, Associated data is processed by absorbing it in blocks of 64 and 28 bits, depending on the variant, and again separated by a call of the permutation. And here, in contrast to the initialization, the permutation has only 6 rounds for performance reasons. And then, after processing associated data, a constant is XORed to the capacity part for domain separation. Processing associated data is followed by encryption of the plaintext. Here again, at each iteration, a plaintext block of 64 or again 128 bits is processed by XORing it to the read part of ASCII and then squeezing out the ciphertext again of R bits, either 64 and 28 bits. And then after the last plaintext block has been processed, there is a finalization where again one XORs the key to the capacity part and then applies 12 rounds of the ASCII permutation, and then again there is an XOR with the key before outputting the tag of 28 bits. And again, this is something which is typically for ASCII. In ASCII, this finalization is again keyed, which is usually not done in the regular sponge construction. However, this keying of the finalization as well as in the initialization has some advantages. First of all, it gives some robustness against state recovery attacks. So even if due to some implementation errors or implementation attacks, one might be able to recover the internal state of ASCII, it's still not possible to recover the key. And also keying the initialization finalization allows for so-called leveled implementations as recently proposed by FX and others, which reduces the cost for side channel protection in some application. So how does the permutation of ASCII look like? It basically operates on a state of 5 64-bit words where the S box, the nonlinear function, is applied over the columns, and over the rows there is a linear layer which operates on words of 64 bits. So the permutation of ASCII is quite simple. It's based on the Ketchak S box in the middle part, and we only added an affine layer at the beginning at the end to increase the branch number of the S box, which is needed in ASCII for the interaction with our linear layer to achieve good diffusion. And the nice thing of the Ketchak S box is that it can be implemented very efficiently in a bit-less manner in the case of ASCII 64-bit words in parallel, and also has a low degree of only 1 AND gate per bit, which allows very efficient implementation of masking of the S box, reducing again the overhead for implementations where side channel protection is needed. So for the linear layer, we use a very simple function, which is very similar to the sigma functions used in SHA-2, where one basically takes the 64-bit word and XORs it with itself, rotated by different offsets, which can be implemented very efficiently with only a few operations. In particular, on ARM, this only needs 2 instructions. And the diffusion is again quite good since this provides a branch number of 4, which results in a quite good diffusion and security of the ASCII run function and permutation. So what about security? We investigated differential and linear properties of the ASCII permutation, and what can be seen here at the analysis we provided and published data group that already for 5 rounds we could not find any differential or linear trail with less than 64 active S boxes, which shows that ASCON provides a huge security margin against differential and linear cryptanalysis. Besides this, we also looked at other attack vectors on the ASCON permutation, like cube-like attacks exploiting the low degree of the S box. Here, the best attack that could be found by us and others is on 7 out of 12 rounds of the initialization of ASCON with a complexity of 2 to the 104. And by doing a differential linear attack on the finalization, one could attack 5 rounds of the finalization of ASCON with a complexity close to 2 to the 46, which I think was recently slightly improved to a lower complexity, but still so far no one can attack more than 5 rounds of the finalization with practical complexity. These are the best known attacks on ASCON at the moment, since it was published 6 years ago. But of course, people also looked at many other properties of ASCON, providing detailed security analysis. And at this point here, I want to thank all researchers contributing to the security analysis of ASCON. Here you see the most interesting publications dealing with security analysis of ASCON. So many thanks to all the people doing this analysis and helping to get a better understanding of the security margin of ASCON. So as I said before, we also added an hash function, ASCON hash and ASCON XOF, which basically is a straightforward implementation of the sponge construction using a 320-bit states and 256-bit capacity. So here, as it's done in Catshark or many other sponge constructions, we absorb the message in 64 bits and apply 12 rounds of the ASCON permutation in the absorbing phase. And then the attack is constructed by squeezing 64 bits of the state in each iteration until the hash value of 256 bits is reached for ASCON hash, or more bits for ASCON XOF, which produces an arbitrary length output. Again, we looked at the security of the hash function, and the best known attacks on the hash function so far are for 2 out of 12 rounds and collision attack by Wang et al. And for ASCON XOF, for 64 bits, where one squeezes only one word at the output generation of the XOF function, the best attack is on 6 out of 12 rounds, which is a complexity to the 63.3, which is very close to the general complexity of 2 to the 64. However, this cannot be extended to ASCON XOF with larger output sizes. So what about implementation? As I said before, ASCON was designed to be very efficient in hardware and software. In particular, we wanted to have something which gives you a high speed on high-end platforms like high-end servers, which are used in IoT, or some hardware support in those servers using FPGAs. On the other side, we wanted to have something which can be implemented with very low overhead on constrained devices like RFID tags or IoT devices with low area and code size. So what about software? So on high-end Intel or AMD processors, ASCON 128 has a performance for long messages close to 10 to 11 cycles per byte, and ASCON 128 is close to 7 cycles per byte. Similar on the high-end ARM platform with 64-bit architecture, performance of ASCON 128 is around 11 cycles and 128A around 7 cycles. So for hardware implementation, many thanks to a former colleague of mine, Hannes Groß, doing several different implementations here. One could implement ASCON with a footprint around 7 kilogates and a throughput of 5,000 megabytes per second in a round-based implementation. And this can be increased the throughput of 13,000 megabytes per second, having a much larger footprint of around 25 kilogates. And there's also a small variant with around 2 to 3 kilogates, but having a much lower throughput of 40 megabytes per second. But more important, as I said before, the design of ASCON allows very small implementations in hardware where side channel protection is needed, and there exists again three variants, harness the threshold implementations and the round-based implementation with around 30 kilogates, which is quite small for authenticated encryption schemes, can achieve a throughput about 3,700 megabytes per second. And again, a very fast implementation around 9 megabytes per second, but having a much larger footprint of 120 kilogates. And the small variant has around 8 kilogates and a throughput of 40 megabytes per second. So what are the main features of ASCON? So it's very small in hardware. It's efficient in software, in particular also on high-end servers, which might be the case for applications in IoT, where you have many devices communicating with one high-end server. It provides natural side channel protection, so the bit sliced SBox and the low degree allows very nice protected implementations in hardware and software, and also gives natural protection against, for instance, cache timing attacks. It has limited damage in misuse settings due to the fact that the initialization finalization is keyed, even though an attacker might be able to recover the internal state due to the implementation errors or reusing nonces. This does not immediately lead to key recovery attacks, which again increases the robustness of ASCON against all kind of implementation attacks. It has low overhead for short messages due to this very cheap initialization and finalization of ASCON. So let me summarize. ASCON was designed 2014. It received a lot of attention in the CISA competition. It's well analyzed and understood by the cryptographic community, and results indicate that ASCON provides a large security margin against all known of cryptographic attacks. It's very efficient on constrained devices in both software and hardware, and provides some natural side channel protection due to the slice definition of the ASCON permutation against cache timing attacks, but also the low degree of the SBox allows very efficient mask implementation. And it's very fast on modern CPUs, around 10 cycles per byte on high-end servers of Intel and AMD, and also on high-end ARM 64 bits, the performance is very close to 11 cycles per byte, which makes ASCON the perfect choice for IoT applications. If you're interested in ASCON, you can find further information on ASCON and all kind of implementations and comparison of implementations on our webpage, ascon.iaek.geograz.at. While ASCON is a dedicated authenticated encryption scheme, I want now to discuss ISAP, which is leakage resilient authenticated encryption mode that was designed to provide some robustness against side channel attacks by design. ISAP is joint work with Christoph, Maria, Stefan, Bart, Thomas, and Robert. And its design was mainly motivated by side channel attacks. Of course, typically side channel attacks are something that is coped with on implementation level by implementing some dedicated countermeasures like hiding or masking. And many of these candidates in round two of this competition are designed to reduce this overhead for implementing masking and hiding for authenticated encryption. Some examples are, of course, Ascon, but also the scheme Gimli, Kodiak, Pyjama Mask, and many others. However, the question we ask ourselves in the design of ISAP was, can we do more than just choosing the building blocks of the authenticated encryption scheme in a way that countermeasures against masking can be implemented with a low overhead? In particular, we ask ourselves, can we add some robustness against implementation attacks already on an algorithmic level, namely the mode of operation? And ISAP is the result of some work done around 2017, where we first published the first version of ISAP at FSE 2017, and in parallel to our efforts for designing and leakage resilient authenticated encryption schemes, many other teams have been working on in a similar direction. For instance, the scheme proposed by Pavel, Martin, Oswald, and Stam at AsiaCup 2017, where they proposed also some leakage resilient encryption scheme, or the work of Berti, Pereira, Peters, and Standard, which also proposed some leakage resilient encryption schemes at FSE 2018. So ISAP is designed to give some robustness against differential power analysis already on an algorithmic level for both encryption and decryption. It's solely based on the sponge construction that, as I said before, was proposed by Demon et al. In the Shafri competition in the design of Kaczak, and later extended to build also authenticated encryption schemes in the duplex construction. And as you will see for ISAP, sponges are a very useful tool to also limit the attack surface against certain class of single power analysis attacks. So in general, when we talk about sentinel attack, we talk about simple power analysis, where basically an attacker observes the device processing the same input several times or only a very few inputs, and then tries, based on the set channel information, for instance the power consumption of the device or some timing information, to retrieve some information about the secret key that was used to process the data. And what's basically done is one tries to interpret a measurement curve to get some information about the key. And contrast to that, in differential power analysis, basically one observes many different power traces or timing information for many different inputs, and then use some statistics to retrieve some information about the key. And typically in a differential power analysis where one can observe the processing of many different inputs, less information is needed about the particular implementation of the scheme for doing the attack. Of course, in practice, on the security controller, one implements several countermeasures against both differential and simple power analysis, for instance, by using some hiding or masking scheme in the implementation. So the question is, why do we care about set channel attacks in practice? So here I have two examples in academia, a paper published by 2016 by Moradi et al., where they basically showed how a set channel attack can be used to break the bitstream encryption of Xilinx FPGAs, which are used to encrypt the bitstream. And another work by Shamir et al., which basically showed that with an DPA attack, one can recover the secret key that are used in some smart lamps to retrieve the secret key, which can be used to deploy your own firmware update or to manipulate the function of the scheme. So the question we wanted to answer with ASAP is, can we do more than only using a permutation or an S-box, which is easy to mask? Can we increase robustness against differential power analysis already on an algorithmic level using a suitable mode of operation? So there has been some work regarding this in the past, which is typically referred to as fresh rekeying for some application. So for instance, consider one has some reader and attack, like it's typically the case for RFID, and then one can use a rekeying scheme to increase the robustness against differential power analysis. And the idea is actually very simple. Instead of masking the block cipher E, which is used for encryption and decryption, one can use an additional function, a so-called rekeying function G, which is typically much cheaper to protect against session attacks than the block cipher itself. And then based on a nonce, which is randomly generated on the tag, this nonce and the master key is used to derive a key K star, which is then used for the encryption of the plain text, which is then sent to the reader. And on the reader, the same is done for the nonce. Here on the reader side, since the nonce is only chosen on the text side, there is some side channel protection of the block cipher needed as well. However, on the reader, which is typically much more powerful, masking can be implemented more efficiently. But on the tag, this rekeying function allows to move the complexity of masking the block cipher to the complexity of masking this rekeying function, since there is always a unique random nonce, which is used for deriving the key star. One can move the attack surface from a differential power analysis to a simple power analysis, and it's sufficient to mask only this rekeying function G. This can also be extended to a mutual authentication setting. As I said before, since on the reader side the nonce is input over an unsecure channel and can repeat, the reader needs to be implemented, needs some kind of DPI protection on implementation level. This can be this cost can be reduced as well, namely by using now two nonces, NA and NB. NA is generated by party 1 and B is generated by party 2, and then both nonces are used in this rekey function G to produce the session key K star. And then again, the complexity of masking the block cipher is shifted to this rekeying function, which is supposed to be easier to mask than the block cipher itself. And since NA and NB are randomly generated on both devices, so either NA by party 1 or NB by party 2, there's also always some freshness, and K star is never repeating. However, the question is, how can we use this for authenticated encryption, or in particular, what's about storage of storing data? Now again, assume we have this device, we generate the nonce and use the master key and the free key function G to get the key K star, use this to encrypt the plain text and receive the ciphertext, and then store the ciphertext, for instance, on the hard disk. So as you can see here, since for each encryption we choose a new random nonce n, decryption is fine. So if the rekeying function G is secure against TP attacks, so is the whole encryption procedure due to this rekeying principle. However, decryption now gets critical. Since for decrypting data, the device takes the ciphertext and the nonce from the hard disk and decrypts the data, the scheme gets vulnerable to TPA attacks, since an attacker can modify the nonce and the ciphertext on the hard disk and ensure that always the same nonce is used in the rekeying function, and thus key star is repeating, getting the typical setting for a differential power analysis. So the main question is, how can we protect the decryption for storing data or building an authenticated encryption scheme based on rekeying? So first option is to protect the implementation of the decryption by some DB countermeasures, but of course this is very costly and actually makes the use of this rekeying function gene used for encryption some kind of obsolete, since it doesn't make sense to have a side-channel protected implementation of decryption and using rekeying for encryption is typically not a very good trade-off. Of course, we could also limit the number of decryption to one, for instance, but then we need to keep track of all nonces that has been used before in any of the decryptions, which is actually practically not very feasible. We can re-encrypt data, so all the time when reading data from the hard disk, we can re-encrypt it with another nonce, which is again very costly. And again, we cannot guarantee that no one is tampering with the data stored on the hard disk. It's also very time consuming and actually has many fallbacks which has to be considered. So we want to have a more efficient solution here. So what we basically want to achieve is we want to retain the principle of fresh keying, but also allowing multiple decryption. And by doing this, we would get some scheme that is robust against TPA attacks in the storage setting, but also for application with unidirectional or broadcast encryption, like firmware updates, one would get TPA security by allowing multiple decryption but still being able to use this idea of fresh keying proposed by Medved et al. At Africa Crypt. So what's the main idea of ISAP for protecting the decryption? So the idea is to bind the session key somehow to the data that is decrypted. And what we do here is we do basically an hash 10 max scheme. So the idea is that we take the nonce and the ciphertext and we hash this, and then we get basically the value h, which is used as input to the rekeying function g. And then based on this hash value, which is unpredictable, we derive the session key k star, which is then used to compute the tag of the authenticated encryption scheme. And once the tag is verified, meaning that the nonce in the ciphertext is correct, we use the nonce and the key to derive the decryption key, which is then used for decrypting the ciphertext to get the plain text P. This has several benefits. However, for the scheme to be implemented, we now need an hash function, H, a rekeying function, a MAC function, and a decryption function, which typically might result in a very expensive scheme needing a lot of area and code size. However, we can optimize this. And here we benefit of the sponge construction. So the sponge construction is well studied and analyzed, and it allows to implement a wide range of primitives by using only one permutation. So sponge construction can be used to build an hash function, and MAC, and an encryption scheme with the use of only one permutation. And there is no key schedule, and the key is only used once in a sponge, which is one of the main requirements for building a leakage resilient authenticated encryption scheme. And moreover, the sponge construction, as you will see later on, allows a very simple and neat way to model side channel leakage in the mode of operation. However, before discussing this, let's have a look how authentication verification now would look like using the sponge construction. So for the authentication verification, we need an hash function, a rekeying function, and a MAC. So first, the nonce and the ciphertext is hashed. That's the upper line here of the sponge construction, and the output y, which is the output of the hash function, is then used as input to this rekeying function g, together with the master key ka, to derive ka star, which is then the key that is used for the MAC. For the MAC, we use now suffix MAC, where we basically first process the message, and namely in our case the nonce and the ciphertext, then using the duplex construction, and then we take the session key ka star to produce the tag. And then I think here by using the suffix MAC construction here in the sponge, we see that actually the hash function and the lower part, the MAC, are having the same input for the first line, which means we can actually simplify the construction from before, getting something like this. So we now only process the nonce and the ciphertext once, and then we take the output of the permutation as input to this rekeying function j, XOR it again, and then we do a final permutation called the produce the tag, which now is much more efficient than the previous construction and gives you the same level of security. And actually, the construction with the rekeying function g can be also simplified, having something like this here, which basically now is a simple construction of using suffix MAC instead of this hashed and MAC parting we have seen before. So the only thing we need to decide now here for the authentication and verification part of ASAP is how to choose this rekeying function G. Of course, there are several possibilities of doing that. So in literature, Medved et al. Proposed using, for instance, a modular multiplication, which is very nice to implement in a mask way in software and hardware, or using something based on learning with errors, or, which is the option we prefer, is the scheme proposed a few years ago at DATE, which basically uses, again, the sponge construction. So the idea is actually very simple. So instead of absorbing always R bits in the rate part of the sponge, the idea is to reduce this rate to the minimum of a single bit. And then the construction one gets by doing this is very similar to the classical GGM construction proposed for key derivation many years before. And this way, the number of measurements an attacker can do for each permutation call is limited to two inputs, namely either y one is 0, 1 for the first permutation, and for the second call, it's again two measurements and so on. And since this permutation is supposed to be an idle permutation, combining the leakage of the two permutation or is supposed to be very hard. So now we have chosen the rekeying function and the MAC for our encryption scheme. Encryption can be done in a straightforward way. Basically, one is doing the same. One initializes the state with the key and the initial value, and then similar to the rekeying function, the nonce is only processed in single bits before doing the encryption on more bits than before. So this picture is what we have proposed in ISAP version 1 and in ISAP version 2. At the input of the rekeying function, here some bits are truncated to increase the robustness against side channel and fault attacks, but also to be able to provide a security proof. So as I said before, choosing sponges has several advantages, and one advantage is that it provides a very neat way to model side channel leakage in a sponge construction. And this can be seen as follows. So if we consider two permutation calls with a rate, for instance, of 1 bit in the case of the rekeying function, then an attacker might be able to also learn a few bits from the permutation itself, namely L and L plus 1 bits due to the leakage of the permutation. And this can be modeled in an abstract way for sponges by considering the combined leakage L1 Li plus Li plus 1 as part of the rate part, the public part of the permutation call, and reduced capacity C prime, which gives you now a very nice tool to argue about side channel leakage in sponges. And indeed, recently many people have been working on proving leakage resilient construction, leakage resilience of the duplex construction or sponges in general. So first of all, of course, Christoph and Bart showed leakage resilience of the duplex construction and also started the security of suffix keyed sponges as used in ISAP at FSE 2008. And in parallel, the Christoph and Bart also showed some proof for the leakage resilient of the ISAP mode of operation, which they presented at the NIST workshop at last year at NIST, and which will be also published in the special issue of TOSC for lightweight authenticated encryption as part of ASAP version 2. And in parallel, also others showed leakage resilient of sponges at AsiaCrypt 2019, and in parallel to Christoph and Bart, also Go, Pereira, Peters, and Standard showed leakage resilience of ISAP at FSE 2020. So as I said before, we have proposed this nice mode of ISAP, which is solely based on sponges, which gives you some higher robustness against side channel attacks, which is proven secure also in the leakage resilient model. And for implementing mode of operation, we propose two instances, one based on ASCON and the other one based on the Kaczak permutation with 400 bits. And here again, we benefit that both Kaczak and ASCON has been well analyzed in the last 6 years. So we benefit from existing security analysis of those two permutation. So in summary, ISAP is an authenticated encryption scheme following the NIST call. It provides robustness against DPA attacks on an algorithmic level, which significantly decreases the implementation cost in hardware and software for applications where some kind of side channel protection is needed. and it enables several nice use cases, as discussed before, like multiple decryption of stored data. For instance, this use case we have discussed before for encrypting FPGA bitstream files, but also unidirectional broadcast communication like firmware updates where typically some kind of side channel robustness is needed, but performance is often not so important. So that's all. If you're interested in ISAP, please have a look at our webpage. There is a nice summary of the existing analysis of ISAP and the security proofs of Christoph and Bart, as well as many implementation results by our team and also other teams implementing ISAP. Thank you for your attention.